All right, so we're talking about the area of a sector, right?
Yeah.
So area of a sector is equal to some arc, let's call it x for now, divided by 360 times pi r squared, right?
Yep.
In this formula, how many variables do you have?
3. 3.
How many unknown quantities do you have?
Oh, 2.
How many unknown quantities do you have?
1.
You have 3.
I said in the beginning. You said that was wrong.
I didn't say anything.
Area?
Yeah. That's unknown. That's unknown. And that's unknown. Okay? Every formula you ever come across, the left-hand side, the side that is isolated, is still an unknown, right? And it's unknown until you plug in x and you plug in r. Okay? So, what are the components that they're allowing me to plug in here? Okay, they give me x. What's x in this case? 90. So I plug in 90. Okay, what else do I know?
The area.
I know the area. I know area is 64 pi, right? And r is what I don't know. R is what I'm looking for, right? That is something that you guys got to kind of wrap your head around, because beyond this class, we start doing story problems a lot of times in like advanced math, algebra 2, integrated 3, stats, calculus. Just because the formula is defined A equals whatever, you're not always finding A. Does that make sense? Okay. Especially a lot of times when we start talking about finances, you're not necessarily interested in what the formula is set up to solve for. It is maybe the thing that we look for the most often. Okay. We look for A, the area, a lot. Okay. So that's why this formula is set up the way it is. But if I was looking for the radius, just kind of humor me here. And you guys have done this in Algebra 1. Maybe not with formulas of this nature, but we could kind of manipulate this thing to say, okay, I can solve this thing for r in this format. I could take A, multiply it by 360 degrees. Would that give me x times pi times r squared? Multiply both sides by 360, right? Could I then divide both sides by x pi? So it has something like that. That is equal to r squared, right? So r would then be the square root of that, wouldn't it? So in that area formula, I have, with my algebra skills, an additional formula that I could come up with to find r. You guys did it all the time in like 7th and 8th grade math when you did distance is equal to rate times time, right? Were you always interested in distance? No, sometimes you're interested in distance divided by rate gives you time, right? Okay. Or sometimes you are interested in distance divided by time equals r. You can manipulate through your order of operations and your algebra skills any formula you have and solve for any variable inside that formula. Now, would anybody want to memorize that the radius of a sector is equal to the square root of its area times 360 divided by pi over x? No, that's kind of, it's messy, all right? So if I ever need that, we can develop it. And the reason we don't memorize that is because we don't ask this question very often. Okay, so we're going to say, I'm going to kind of backtrack here. I'll leave that there, because we're going to see then in a moment if it gives me the same results that I'm interested in here. Our area, you said, was 64 pi, right? That is equal to, we said 90 over 360 times pi r squared. What's 90 divided by 360 give me? 1/4, so I have 1/4 pi r squared equals 64 pi. How can I get rid of this 1/4? Times everything by 4. So it gives me 256. Okay, pi is equal to pi r squared. How do I get rid of that coefficient of pi here? Divide by pi. Divide by pi. So it gives me 256 is equal to r squared. Now what would I do? Yep, square root that. And We are lucky because square root of 256 is 16. Okay? So the radius of the circle is 16. Let's see if that gives me the same thing here. Okay? If I take, now, let me just use Desmos to type all this in for us. But if I type in square root of, what do we have, 49 pi times 360, and divide that. Oh, 49. Wait, I think we did 49 in the last class. Sorry. 64. Relax. Jeez. And then we did what? Pi times x, which was 90, right? To give us 16? All right. So that formula could be used if you wanted to. But I don't think we should want to use that and learn that because it's going to add to the things that we got to hopefully not memorize, but just adds congestion to our formulas if we try to memorize one more or learn one more like this. Is that doable?
Yeah.
Somebody asked about this one. All right, so it's kind of important, I think, Cameron, to, as we go over these questions, if you struggled on them, maybe to write them down how we do them, because guess what's going to happen tonight?
We're gonna do homework assignment over it.
You're going to get the same types of questions. That we do. Huh? No. Unless you memorize your open notes. Here we've got this concept. We're trying to find that blue region. That's called a segment of a circle. There's not a general formula for this, and it's an irregular shape. So there's not one predefined, just these are my variables, these are the things I plug in, and it spits out the area. You have to kind of develop a plan of other area formulas you mess around with to generate this area.
Can I write down a formula that would work for this?
Huh?
Can I write down the formula that would work for this?
Say that again?
Can I write down the formula that would work for this? Because there is a formula that would use.
Yeah, no.
Okay, well, let me write it.
I don't mind.
Janika, where'd you get your jeans? This is it.
They only sold you half of them.
I mean, same. Do you have a marker? Maybe
Just use your finger. Uh-huh.
But I can't remember like where.
Put pi in there in front of your R squared.
Okay.
And put a minus sign after your R squared.
Minus, yeah.
Okay, so what that is, and that's if you want to learn that formula, that's fine. But we already know those individually because isn't this thing here the area of a sector? Isn't this thing here the area of a triangle? And isn't this minus sign here that minus sign? So if you want, then that's fine, okay? But there as we move through geometry and other courses that we want to kind of develop a plan to attack a problem, you're going to have to take these individual kind of smaller components, area of sector, area of triangle, area of circles, that kind of stuff, and reorganize them through your order of operations to determine how to find, in this case, maybe an area or at some point a volume. But yes, if you want to learn that formula there is the formula for the area of a segment, by all means, go ahead and learn it. But my hopes are is that we understand that we've already memorized this at a smaller stage and other problems. We've already used this and learned this in smaller stage and other problems. This problem is just the combination of those things together. Okay? But good. Okay? So, and there's also, there's a lot of stuff going on in this problem. There's a lot of class lectures that we go through and realize that maybe in addressing this problem, there's 3 or 4 or 5 chapters of information that we need to have so that we can progress through this accurately. Okay? First thing's finding the area of the sector. Okay? So I write down my plan, kind of like I have up here, and then I just start finding those individual components. So I'm going to look at this, I'm going to do that, because I can do that one problem. I've done that, and you've shown that you can do that in previous questions in this assignment. So if I can find the area of a sector, I'm well on my way to getting this question answered. So I find the area of the sector. When we talk about the area of the sector, we're talking now about everything that's blue, right? Okay? So everything that would be blue, like Jenica told us, it would be the arc, which is 60 degrees, divided by 360 times the area of the circle. So pi r squared would be 18 squared, right? So I get 60 divided by 360 is 1/6. Anybody know what 18 squared is? Good, 324. 1/6 of 324, 54. Great. So I get 54 pi. And that's the area of everything that's blue, right? Now I'm going to find the area of the triangle. We know that's 1/2 BH. Okay? Or we could look at this and realize that this is a special type of triangle. Is this a 60-degree angle right here? Is this isosceles? So is that 60 and that 60? You guys remember saying the area of an equilateral triangle was equal to s squared radical 3 over 4? It actually allows us to do this problem a lot quicker, because s is 18 now. So 324 radical 3 over 4, and 324 divided by 4, 81. 81 radical 3 would be the area of that triangle. I'll go through another way of finding that area, but now that I have those two areas, what would I do with them to find the blue region? Yeah, I'm gonna finish this plan, which I'd find these individual components. I've done that. It says subtract them. So I go 54 pi minus 81 radical 3, and that is your exact answer. The question says round it to nearest tenths, hundredths, whatever. You can now do that with your calculator. Okay? In the event, because this area formula right here was only special, and I could only use that because this was 60 degrees. You're going to see in your homework that could be 120. I think there was one that was 55. That will change. Okay, so I want to give you kind of the general way of finding that area. And we've done this. You guys have done this many a times. If I look at this triangle right here, we need to use 1/2 BH. 1/2 BH. And there's 3 different H's here that you could use. But the most obvious and easiest to find, regardless of what that 60 is that altitude right there. Does that make sense? So if it's 120 degrees, if it's 40 degrees, if it's 72.5 degrees, you're going to use that altitude. Okay? Because if I use that altitude, what does it make this angle right here where my cursor is? 30 degrees. And this would be 60, right? Making then this 2n. Because it's a 30, 60, 90 triangle now, right? N then has to be 9. And that n would be that little red distance, correct? Would you guys agree that this distance right here is going to be n radical 3? So 9 radical 3, right? So the blue distance, 9 radical 3, for the triangle is your altitude. What would your base be? If this red distance is 9, your base would be 18. Okay? Well, 9 times 18 times 1/2. What's 18 times 1/2? 9. What's 9 times 9 then? Does that give me the same area that I had found using s squared radical 3 over 4? Okay? That's the process that you would use all the time with regardless of that angle. Now, sometimes that angle, they're going to give you that angle to a lot of times be 90, 60, 120. And the reason they're doing that is because when I draw that altitude, it takes a 90 and reduces to 45. It takes a 60 and reduces to 30. It takes a 120 and reduces to 60. So every time I generate special right triangles on the inside there. Does that make sense? So that's why you get those numbers a lot. But that number could be 28. Okay? And when I cut that in half, I get 14, right? Is there a triangle that we have that has an angle of 14 degrees in it? Special right triangle with a 14-degree angle? No. So what do we always turn to then? That special right triangles don't work for us. SOHCAHTOA. Okay? And now allow you to find H and B using sine, cosine, and tangent. And you progress the exact same way. Okay? Is that all right? Okay. So that problem then is going to then shed light on maybe what we can do on. So this is what I was saying on this one. This could be 70. So now you'd have an interior angle here. And that triangle, that blue angle right there would be 35, right? And you would use SOHCAHTOA then to find the altitude in the base. Yeah, we can get to that. That's the one I was looking for. Good. All right, so I'm going to actually generate a new question. Are they all 120? All right, so looks like everybody's getting the same 120 degrees. This is good. It's a good question to talk about in respect to what you're doing for your homework tonight. All right, so a couple different ways I think you can approach this question. All right, when I look at this question and I see that orange area being the area that I'm interested in, I see a circle and somebody sliced off a piece of that circle. Does that make sense? So if I can find out what the area of that thing that they sliced off of, which would be the segment, which would be that white region, if I can find that area, can I subtract that from the entire circle's area and be left with the orange area? Does that kind of make sense? I'm going to write a plan out here, and we can do this two ways. I'll write the plan out that I visually see. I see taking the area of the circle, okay, and then removing from it the area of that white segment. Does that make sense? Okay. Now, how does this relate to the last question? The last question told us that the area of a segment was the area of a sector minus the area of the triangle, wasn't it? So you see how this plan could look something like that? And now I have the three components that I need to find, and then when I plug them into that general plan, I should be able to subtract them and get my answer. Now you just got to be careful when you do this with your subtraction, because you're subtracting negatives at some point. I want to enlarge this, and for some reason it won't let me. There we go. All right. If I find the area of my circle, that should be something we're pretty adapted to. What would be the area of my circle here? 36 pi. Take my radius and square it, right? Multiply by pi. The area of the sector, again, probably not something terribly difficult here, because it's just your arc divided by 360 times your circle area, isn't it? So your circle you've already found, right? You found your circle to be 36 pi. What was your arc? 120. So I'm getting 1/3 here of 36 pi. What's a third of 36? 12. So we get 12 pi. There's the area of my sector. Now I want to find the area of this triangle. Area of a triangle is 1/2 BH. Okay. We know that that altitude is the one that we're always going to be interested in, regardless of the angle. What would this angle right here be? If that's 120, that's got to be 60. This would be 30, making this my 2 inside, right? So n would turn into 3, and that's my altitude for my triangle. What would this distance right here be? If n is 3, across from 60 would be 3 radical 3. And now what would the entire base be? 6 radical 3. So I'm going to go 1/2 my base of 6 radical 3 times my altitude of 3. So that gives me, that's 18 times 1/2 would be 9, right? 9 radical 3. So now I've got the individual components, correct? I'm going to plug them into this kind of generic setup that I have here. Area of the circle, we said was 36 pi, minus, I'll put my parenthesis, area of a sector was 12 pi, minus the area of the triangle, which was 9 radical 3, right? Now, why did I put parentheses there? Because I'm subtracting a quantity, right? And when you subtract a quantity, this thing's going to turn into 36 pi minus 12 pi, and then what? What should I put here? If I subtract 12 pi, then I'm subtracting the negative 9 radical 3. This should turn into a plus 9 radical 3, doesn't it? And that then ends up giving me 36 minus 12 is 24. So you're saying kind of like what Jenna provided us earlier? Okay, yeah. Or Jenica. Sorry, not Jenna. We had 24 pi plus 9 radical 3. All right, so there's the area. So you're saying what would a general formula for this look like? It would be pi r squared minus, okay, arc over 360 times pi r squared minus 1/2 BH, which ends up being pi r squared minus the arc over 360 times pi r squared plus 1/2 BH. I don't think that's something you're going to want to memorize, right? That's messy. It's a lot of stuff going on. And there's other ways you could write it. You could take pi r squared out of the first 2 terms, that kind of stuff, but I don't know if that's really what we're interested in here. Now, I'm not going to get into the details of that formula, but that formula, once I distribute that negative sign through, that formula ultimately says we actually end up adding this triangle in, don't we? Okay? So what that means to me is that that right there is ultimately producing the area of that sector. Does that make sense? If I add that sector in the red triangle, do I get the overall goal here, the overall question? So somebody was saying in the last class that this is what they did. They took the fact that if this arc is 120, the arc of everything that's orange is 240. So I took 240 times 360 times 36 pi. So when I do that, that's 2/3 right there. 2/3 of 36 is 24. Does that make sense? Okay. So that gave them everything here that I've got is blue. And then they said, well, then I found the area of the triangle, which we find out to be 9 radical 3, and they add that on. Does that give me the same thing we found? And that might be a safer approach because you're not subtracting negatives, but in both of them, you still have to find a segment, an area of a sector, and you have to find the area of that triangle. Okay. For some reason, the area of the triangle is what stumps people a lot, and that's where they struggle with it. Okay. Are there any others on there you guys need to talk about? Conceptually, was this question the same as that question? You want to talk about them? Okay. All right, so what I want to say, those two things are the same. They're the same question. Obviously different numbers, but conceptually they're the same. And you're going to see one in your homework tonight like this. So it does benefit us in regards to talking about. I'm just trying to get one that has different numbers. We did this in the last class, so I don't want to use the same numbers. Huh? You had the one with 14? All right, what kind of shape is the polygon? A square, right? And then the overall question is find the shaded region. The polygon is a square. So what are the side lengths of this square? 28. Okay. So we're going to go 28 squared, right? 28 squared is 784? Okay. Is that all right with everybody? Everybody see that BC would be 28? So DC is 28 because of the notation that we're presented with these markings. Okay. What is this angle right here if this is a square? A right angle. So what is this? If that's a right angle and this here is an arc, what would you know what the... Okay, that would be a 90-degree arc, right? Would that be a 90-degree arc? Would that be a 90-degree arc? Would that be a 90-degree arc? So Cameron, what are you saying that those circles are going to do? Or so those sectors are going to do? Yeah, they add up to a circle. So can I just take the information from this sector, from maybe one of these sectors, and say that R in that sector is 14? And then if I find the area of a circle that has a radius of 14, that would be the area of those 4 regions added together. All right? You know, take scissors and cut those things out. Cut those red regions out and then reorganize them. Do you get a circle? Okay, and we can find the area of that circle by pi r squared. So now what am I going to do with those two numbers if I want to find the blue region? Subtract them. Which one's bigger? Okay, so 784 minus 196 pi. And that's what we're looking for. You can change that to a decimal as you see fit. The next question looks like this. So we got a circle on the inside. Okay. Would you guys make the argument that if I were to look at this picture here, and I draw down that line, and I draw down that, or draw across that line, that maybe that region right there is that region? And then that region is that one? All right, so is it the same problem? It's just that that blue region is reorganized?
Yep.
All right, or the white regions are reorganized. So you would do the same thing. You would find the area of the square, remove from it the area of the circle, and that gives you the region that I'm interested in. That's what we use a lot of times, kind of in the real world, guys. We go out and we use mathematics to model the real world and explain phenomena that occur in the real world, right? In the real world, nothing really turns out really nice, okay? So there's really not usually really nice formulas that I can use to find area. For instance, let's look at the sculptures out there in the courtyard. If I wanted to find the area of iron that took to make those things, there's not a formula for that, right? But I could probably chunk that thing up into a couple different, maybe rectangles, some arcs, some triangles, that kind of stuff, some circular portions, and I could add those together, subtract those, and then find out what the area of that shape is out there, right? And that's what we learn these individual formulas for, so we can condense them through addition, subtraction, maybe multiplication, division, to measure areas of irregular shapes, because that's what we see a lot in nature, in the real world. That being said, we're going to do this stuff again today. We're going to keep